So Andrew, do we have your consent to record the talk and put it on YouTube afterwards?
Yes.
Okay, excellent. Good. So let's go for this last invited talk of ANTS 2020. So it's my pleasure to introduce Andrew Booker. So he's a professor of pure mathematics at the University of Bristol, where he's been working for some time after having done his PhD in the US at Princeton. So Andrew has published articles in a nice collection of journals that cover mathematics and computational mathematics. His topics of interest are vast and include in particular arithmetic geometry and modular forms, L functions, and so on. So his talk today is about the kind of problems that are pretty easy to state, but require a lot more effort to solve, if I may say. And I foresee as well, also judging from the first slide, that although there's 33 in the title, there's also a 42 that comes into play. And so there's a direct reference to the Douglas Adams books, where it takes the computer 7.5 million years to obtain that 42 is actually the answer of like the universe and everything. Now, in his work, I don't think that Andrew required 7.5 million years on a single computer to do a computation. But I think that to do a fair comparison, it will be important to behold the magnitude of the computational effort that was undertaken by Andrew. And I look forward to hearing details about this. So, Andrew, the floor is yours.
Thank you, Emmanuel, and thank you to the organizers for inviting me to take part in this unique event. I'd also like to wish a happy 4th of July to my fellow Americans. Please celebrate safely. Right, so I'm going to speak about the sum of three cubes problem. This is joint work in part with Andrew Sutherland from MIT. And you can see the link to our archive paper, which has just appeared in the archive yesterday. Okay. I'd like to thank Drew for working heroically over the last week to get this paper ready in time. In addition to organizing and running a online conference for hundreds of people and for organizing his own talk. Like Renata, I do wonder when he sleeps. So I'm aware that some of you will have seen Drew's talk in the Number Theory web seminar back in May. But just to assure you, the content will be significantly different. I'm going to focus on the earlier discovery of 33 for the most part. There's a particular story that I want to tell there, a story that, so even now, more than a year after the fact, I still find a bit surreal, and I'd like to relate some of that. I have given a version of this talk once before, last year at a conference in Italy, but there will be some new stuff at the end, if time permits, for those of you who were there. All right, so let me begin. The story of 33 starts with this particular sum. Now, the first time I gave this talk, I toyed briefly with the idea of trying to pull a Frank Nelson Cole and just multiplying it out longhand without saying a word. But of course, practical constraints got in the way. I'm not very well practiced in the Harvey-van der Hoeven algorithm, so I would have to do it the long way. Of course, the talk is on top of that not 5 hours long, and I'd inevitably screw it up anyway. So, but I do think it's interesting to point out that if you let the computer do the hard part, which is the multiplication, okay, then you can add this up in your head. Okay, what I mean is here, let's start in the hundreds place and just add the top two numbers. 0 plus 9 is 9, 4 plus 7 is 11, carry the 1, plus 6 plus 5 is 12, carry the 1 plus 6 plus 5 is 12, carry the 1 plus 3 plus 2 is 6, 5 plus 2 is 7, etc. And you can verify that they add up all the way along. Or rather, since we have two negatives and a positive, they cancel each other out. Now, there's a theorem you might have heard of that says they can't cancel everywhere. Okay, that would be a counterexample to Fermat's last theorem, the cubic case. And indeed, they don't. They cancel everywhere except the last two digits. So what we're left with is 52 minus 19, which is 33. Okay, let me tell you how I came about this. Well, it was a computer, of course, at 9:05 in the morning on February 27th last year. The computer in Bristol found the solution that I've just showed you. And I told several colleagues about it later that day. However, I did not go public with this information. That was on purpose because I actually had a much larger search planned In particular, I was still looking for solutions for some other numbers like 42 that Emmanuel mentioned. Okay, and so that's where things stood for a while until 11 days later, one of my colleagues sent me this. Says, hi Andy, just found this online. Is this the same solution as the one you found? And I thought, uh-oh, that doesn't sound good. Is it possible that I've been scooped? Well, I clicked on the link and very rapidly it got worse. So not only was it the same solution, but it turns out this was all over the internet already. And here's a typical example. This was a tweet from Matt Parker of the Parker Square fame. So he writes, hashtag maths news, 33 is the sum of 3 cubes. And then breakthrough by Tim Browning. Now, as many of you will know, Tim Browning and I were colleagues at Bristol for a number of years, for about 12 years. So we go back a long way. Tim had very recently just defected from Brexit Britain to Austria, right before this incident. Now, Tim's a good guy. In fact, he's the first person I told this news to for reasons that will become clear in a bit. So I knew it must all just be some misunderstanding. So I wrote to Tim to protest. In case you're wondering, yes, there was already a Wikipedia article about Tim's discovery on this. But Tim insisted that he was no leaker. Okay, so there was some confusion initially about how this had happened, right? But eventually we worked it out. So here's Tim's email. Notice he initially tried to deflect blame onto Brady Heron, but before figuring out that it was his stub web page. So remember, Tim had just moved to Vienna. He hadn't set up a web page for himself yet. So he was just testing out. And here was the entirety of Tim's web page at the time. That's what it looked like. Now, you might be thinking, well, obviously, if you put something on the web like this, people will find it. It's going to get out. But I will say, in Tim's defense, I never would have expected the outcome that eventually occurred for a few reasons. One, remember, this was just a test page, okay? So there were no links to it like from his institution homepage. So it wouldn't be so easy to stumble across this. Second, even if you do stumble across it, you'll notice that he hasn't put the answer here. Okay, he hasn't written this equals 33. He's just put this there as kind of an enigma that you have to solve. And that's a non-trivial thing to do, okay? You can't just use any old calculator. In fact, notably, if you copy and paste this into Google's calculator, you get the wrong answer. Okay? So you have to have at least a bit of technical know-how to get this right. And third, even if those two things happen and you get the answer 33, you then have to understand the significance of that. That this was an unsolved problem. And I'm not sure that I would have understood the significance even a few years earlier. Okay, so it took a sequence of improbable things to happen for this to leak. And yet all of those things did happen within about 10 days, as it turns out. Now, I will never know what made Tim Browning decide to copy and paste this particular bit of text for his test web page. But as it turns out, this is a pretty good marketing strategy. So in fact, I would say that Tim is a marketing genius, albeit an accidental one. Okay, so all of this drama unfolded on a Sunday. Tim was quick to set the record straight. And by Monday morning, I was getting calls and emails from journalists. Okay, here's a sampling. There were eventually dozens of articles written about this. And I've listed just 5 here. These are the ones that I did direct interviews for. This one at the bottom is from our university press office. They put out a press release and then it got even wider coverage after that. Now, this is not my first experience with press coverage for something that I did. I had a similar experience about a decade before. What I wasn't used to was the scale of it. So you can see there's some quite mainstream media involved in this. I think we as mathematicians are not used to the public at large taking an interest in what we do. A good manifestation of this was in my interactions with my wife's friends. So, you know, to the extent that I have friends, they're all other mathematicians. My wife, on the other hand, has some friends who are more or less normal people. And around this time, even they started daring to approach me and strike up a conversation. Hey, I heard you did this thing. Congratulations. Most of them were quick to confess that they had no idea what any of it meant, but they felt it was something important. And I wasn't really sure what to say to that. It was just a bizarre experience. So this was the reaction from the popular press. But to be fair, the mathematicians also completely flipped out over this. So for instance, there was this on Math Overflow at the same time. I don't think I can actually drop this microphone, but anyway. This post recounts this story of Tim's webpage and then asks for similar mic drop moments. Okay, and it goes on to compare this incident to Appel and Huckin, the four-color theorem, Newton, Wiles, and then I think below this, Watson and Crick, the discovery of DNA. Now, don't get me wrong, I'm happy to be included in such company, but I do feel like this reaction is maybe just a tad over the top. Okay, so what explains this? Why all of this hoopla over, let's be honest, what is a numerical example of something? Okay, well, for that, you can blame Bjorn Pune. So Bjorn wrote an article called Undecidability in Number Theory for the March 2008 edition of the AMS Notices. And if you get nothing else out of this talk but this, I recommend taking a look at Bjorn's article. It's beautifully written. In fact, I think Bjorn won an award for his exposition on this. And as the title indicates, it's an introductory paper about Hilbert's 10th problem. Okay, what made 33 famous is the opening paragraph, and it went like this. So Bjorn asks, does the equation x cubed plus y cubed plus z cubed equals 29 have a solution in integers? I'll give you a few seconds to think about that. Everybody got it? Okay, yes, 3, 1, 1, for instance. Okay, well then he goes on. How about the equation x cubed plus y cubed plus z cubed equals 30? Again, I'll give you a few seconds. Everybody got it? Okay, yes, it does. Don't feel bad if you didn't get it. So the smallest solution is a bit big. Okay, and in fact, this wasn't known until 1999. There's the smallest solution. Then he asks one more question. How about x cubed plus y cubed plus z cubed equals 33? Well, this is an unsolved problem. Now, you might wonder, why did he skip 31 and 32? Well, it turns out there's a local obstruction in that case, mod 9. So we know the answer there. And indeed, the next interesting case is 33. Now, this is an undeniably cool way to begin an article, right? Bjorn did not win that award for nothing. But what's the point here? So my takeaway from this, or the point that I think Bjorn is making, is that it's incredibly easy to stumble on questions that seem very simple, but that we have no earthly idea how to solve. Okay? And this is an example of that. I think this is an important point to make because mathematicians maybe in general, well, possibly with the exception of set theorists who are used to this kind of thing, but many mathematicians feel that they're immune from these issues of undecidability. Okay? In fact, I remember another Notices article that explicitly made this argument in the case of number theory, that yes, so Hilbert's 10th problem is undecidable. And of course, there are these Diophantine equations out there in lots of variables and enormous coefficients that are undecidable. But surely, those are all contrived. And any number theoretic problem we actually care about will never be like this. Okay, but I'm not on board with that at all, with this idea. In fact, I wouldn't be surprised if there are standard conjectures out there that turn out to be undecidable, okay, especially as they involve thin sequences. Okay, so as an example, are there infinitely many Mersenne primes? We have pretty good heuristics on this that seem to match the data well, but at the same time, nobody has any idea how to attack this analytically. And I mean, the point is, it's about such a thin sequence that whether the answer is yes or no has very little bearing on anything else. Okay, so I wouldn't find it surprising if that was undecidable. Right? This 3 cubes thing is in a similar vein. When there are solutions, we expect the set of them to be very thin, so they're hard to attack analytically. And it's really a brilliant example because it's quite simple. On the one hand, it's close to things that we understand very well, like the sum of three squares, Legendre's theorem. Or if you take two cubes or more cubes, then we at least have partial progress. But with three cubes, nobody has any idea how to attack this kind of thing. Okay, so that's the context for why 33 was a famous number. Now it's confession time. So I'm pretty sure I had read Bjorn's article several years ago, but this example from the first paragraph did not stick in my mind. My introduction to the problem was much more modern, namely YouTube, and more specifically, Numberphile, which is a channel run by this chap called Brady Heron, seen here doing some hard science. Yeah, so Brady is a videographer who works with scientists of many kinds to popularize math and science. And in 2015, he did a video with the aforementioned Tim Browning, who was at Bristol at that time. And Tim made a very nice exposition of this problem of the sum of three cubes problem and the uncorrect problem with 33. Okay. Now I had seen the video around that time and thought a bit about it then, but didn't get very far. My involvement was actually involved more serendipity than anything else. So I ran a math club at my kids' primary school. And I think it was around January of last year. I was looking for some topics to go through with the kids. And so I was watching some of these Numberphile videos. And I stumbled on this 33 one and saw that there's actually a follow-up video, which I hadn't realized before, on 74. And so this is an image of Sandra Husman, who had also seen Tim's video on 33 and got inspired to extend the search. He ran a bigger search and found that, a solution for number 74 for the first time. Okay, and then there was this follow-up video. Upon seeing that, that's really when I got hooked on the problem. And yes, in case you're wondering, we did do this in math club, and the kids added up cubes and saw which numbers they could make under 100. You can make a surprising number of them just by hand. Right. Let me give a bit of the history of this topic before I start diving into algorithms. So this question arguably begins with Riley, who was a schoolmaster in Leeds, and who proved in 1825 that every rational number can be represented as a sum of three rational cubes. His proof was about a page long and described an algorithm for doing this. Nowadays, you can give a one-line proof even using your favorite computer algebra software. So there's an identity that expresses X as a sum of three rational cubes, or indeed over any field not of characteristic 3. You get solutions, and in fact, a one-parameter family of them. Y here can be anything. Okay, and Riley goes on to ask, well, what about over the integers? If you can you express every number as a sum of three integer cubes, every integer? The problem resurfaced again in the early 20th century with these identities of Vera, Brusov, and Mahler that express the numbers 2 and 1 as sums of cubes in infinitely many ways. So X can be taken to be an integer here, and that gives you infinitely many representations. There is a simpler representation of 1 that you could easily cook up. This one's a bit more interesting. Then in 1953, Mordell asked a pretty natural question. Well, we have infinitely many representations for 1 and 2. What about 3? And he notes that there are two single-digit solutions you can write down, 1, 1, 1, 4, 4, negative 5, and their permutations. Are there any others? In fact, he makes this more as an offhand remark in a paper about something else, and says it in an intriguing way. He says, I don't know anything about this, and it must be very difficult indeed to find anything out about other solutions. Well, when a mathematician of the stature of Mordell throws down the gauntlet like that, people pay attention. And so it was only the next year, 1954, when Miller and Woollett programmed the EDSAC at Cambridge to search for solutions to Mordell's question. Okay, and they knew that, well, you know, you look for one number, you're likely to come up empty-handed. So they expanded the search out to all values of k, x cubed plus y cubed plus z cubed equals k, for k up to 100. Okay. Now, since this is an ANTS conference, I will point out that this is very early on for something like this. The EDSAC was one of the first digital computers. It was inaugurated in 1949 and still based on vacuum tubes and mercury delay lines. And undoubtedly this paper, which was published in 1955, was one of the first in computational number theory. This would have made a fine contribution to Ant's -19. But of course, that's not the end of the story. Computer technology advanced rapidly from there, and within a decade, another group of mathematicians ran a bigger search, and they found one more value, representation for one more number under 100. Okay, and then there's a big gap in the literature. It wasn't until almost 30 years later that Heath Brown wrote a paper and conjectured that solutions exist whenever there's no local obstruction, which means K not congruent to plus or minus 4 mod 9. So I said there's a big gap in the literature. I can only find one instance where this problem is mentioned in between, and that's in the first edition of Guy's Unsolved Problems in Number Theory. It's, I think, 1984. Just mentioned this as a question. He doesn't take a stance on it one way or the other. Part of what explains that is that the group in the 60s actually conjectured the opposite of Heath Brown's conjecture. They conjectured that at least some of the numbers that they had not yet found would not have any representations. If math reviews are anything to go by, then that convinced at least some people that it was fruitless to do any further work on this. But Heath Brown in '92 said, well, hang on, remember, if there are solutions, they're going to be very sparse. Okay, so we shouldn't give up on this. The first solution might be enormous. And very soon after that, there was an explosion of numerical work on this, so much so that I had to put it in small font. Okay, from 1993 on up to 2016, where Huysman ran Elsenhans and Janold's implementation of Elke's algorithm, okay, that I'll mention briefly. And he found solutions for every value of K under 1,000 of height up to 10 to the 15. Okay. Right, so let me quickly mention Elke's algorithm. In the interest of time, I'm not going to go through a detailed description of this. Maybe I'll just say the highlights. So Elke's algorithm finds for you all solutions of height up to B, so where the maximum variable is bounded by B, and not just for a single number, but for every value of K up to the same height bound, B. And it does all of that in quasi-linear time in B, B times some power of log. So that's pretty impressive. In fact, it's up to the power of log, it's best possible. Okay, because we expect there to be about B log B such solutions, right? The main idea is LLL algorithm, so you could think of this as an analytic approach to this problem. So this is pretty hard to beat. As I said, it's close to best possible, but it's fair to ask, well, what if I don't care about every value of K, but I have a specific target one, like K equals 33? Can you do better than this? Well, then it turns out you can. Okay, with a more algebraic approach. So let me describe that briefly. So let's suppose that we have a solution, x cubed plus y cubed plus z cubed equals k, or we're looking for one. And without loss of generality, I can order the variables in decreasing size. Right. Then what I'll do is I'll take the smallest variable over to the other side. So we write k minus z cubed is x cubed plus y cubed. The point of doing this is this has an obvious linear factor, which is x plus y. And now the idea is to take this x plus y as a parameter that we then fiber over, okay? Or in fact, you have one more bit of information, which is that the sign of x plus y is the same as the sign of k minus z cubed, okay? So it's enough to work with the absolute value. So I'll call that d, the absolute value of x plus y. Then I divide both sides by d, and that gives you a quadratic equation for x and y. We also have the linear relation between x and y and d. Okay? Combine those two together, solve out with the quadratic formula, and you get this formula for x and y in terms of z and d. Okay? Now this immediately suggests an algorithm. You simply run through every possible value of z up to some height. Okay? And then d is constrained to be a divisor of k minus z cubed. There aren't many of those, so you just run through all possibilities and to see which, if any, make x and y in this formula integral. Okay. Now the interesting thing to note is that this is already a quasi-linear algorithm if you accept the standard heuristics for the running time of integer factorization. Okay. Another interesting thing to note is that the running time only depends on the size of the smallest variable. Okay, so it only matters what the size of Z is, and as opposed to the maximum, which we had in LP's algorithm. This always makes at least a constant factor difference. So except for finitely many solutions, we know that the largest variable is always at least the cube root of 2 times the smallest. And in many cases, it turns out, there is a much greater discrepancy. The maximum can be much larger than the minimum, and we'll see a case of that later. And then this gives a big practical boost in the algorithm. Okay, now I can't say something like, you know, this is quasi-linear at a dance conference without inevitable questions like this. I mean, so yes, it might be quasi-linear, but that's a pretty fat epsilon, right? Factoring might be sub-exponential, but of course it's expensive in practice and should be avoided. So for that reason, it's better to turn things around. And instead of running through Z and then solving for D by factoring, you instead run through D and then you solve for Z, satisfying this congruence. So Z is a cube root of K modulo D, right? So if you've taught number theory 101, you know how to do this. So you can, by the Chinese remainder theorem, you first reduce to prime power values of D. And then with Hensel's lemma, you reduce that further down to primes. So the main problem you need to solve quickly is to find cube roots of K mod P for primes P. Now, you might complain at this point that I've said two contradictory things. One is that you should avoid factoring, and the other is this reduction. Obviously, we need to know the prime factors of D in order to do this, right? So what gives? Well, there's a difference between these two. In one case, you're factoring a sparse set of numbers. In principle, you could apply something like Bernstein's algorithm to amortize the complexity of that, but it will never be anywhere close to what you can do when you're factoring every single number, which you can just do with like the sieve of Eratosthenes. Or even better, change your perspective and realize that you don't have to go through the values of D in linear order. Instead, you can just recurse over all possible prime factorizations, okay? And then you never factor anything. In fact, you never even divide anything. You just multiply the numbers up, okay? All right, so that's the basic algorithm. Let me, for the remainder of this, I'm going to focus on a particular case where K is plus or minus 3 mod 9. It turns out that that all of the hardest numbers, all of the small candidates for which we don't know solutions satisfy this. That's not an accident. So it turns out that there's a near obstruction in this case. And all of the variables are forced into the same congruence class mod 3 by this. Using that fact, so once you know X and Y mod 3, you know there's sum mod 3. And using that, you can then work out what the sign of Z has to be from the Legendre symbol, okay, once you know D. Okay, to make a long story short, you then end up with this system. So you replace the 3 cubes equation by well, 2 new variables, D and Z, and you want to run over all solutions to the following system. So Z's that have the given sign and that are cube roots of K modulo D. This last line here, this is just the discriminant of that quadratic that I wrote down before. So if I want integer solutions, this should be a square. And we want Z below our height bound of B. And finally, so I didn't explain this, but you can work out a bound on D given the size of Z, right? And it works like this. So D goes up to the cube root of 2 minus 1 times Z. This number cube root of 2 minus 1 is about 0.26. So very roughly speaking, in the whole algorithm, D goes up to about B over 4. All right, so that's just the main system. You can do then a little local analysis at primes dividing 2 and 3, and you get for free some congruence constraints. So for instance, once you fix the value of D, Z is determined mod 18. And so already the search is, you know, this helps practically, the search is 18 times faster than it would be just completely naively. All right, now let's analyze the complexity of this. The problem is, so even with these tricks like the mod 18 thing that I mentioned, there are at least a constant times B log B candidate pair satisfying the first line of the system. So that was everything without the square test, okay, everything except the square test. That means that if you want to get better than O of B log B running time, then you're going to have to do something to reduce the size of the search space. Okay, so I solved this with a time space trade-off. the idea is this. So if this number delta, which is the discriminant, is a square, then in particular it's a square mod p for every p. So this Legendre symbol, delta over p, is either 0 or 1 for any odd prime p. Now we just leverage this as many times as we can. So we use all the small primes. So I'll set m equal to the product of primes from 5 up to some parameter capital P that will optimize. And then I pre-compute all of those z's mod m that satisfy this constraint for every prime dividing the modulus. Okay, so you can pre-compute those. Of course, that comes with some setup cost. The setup cost is roughly on the order of m. But you expect it to reduce the number of z's you have to look at by a factor of 2 to the omega of m, okay, on average. Right? So the thinking here is each Legendre symbol should roughly cut in half the number of solutions. Okay. Now you just, to optimize, you balance these two things. And what you find is you optimally want to choose p about log log b, log 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 b. Now this is a proper analytic number theory talk. And you end up with a heuristic total running time of b log log b log 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 b. This is already pretty close to linear. And if you wait 40-something years, then Harvey and van der Hoeven will remove the log-log factors for you. Okay, but already it's pretty close to linear, and that's what you observe in practice, linear behavior of this. That's assuming you do everything else correctly. Okay, so there's many practical issues that come into play here. Maybe the most important practical point is that 64-bit arithmetic is now ubiquitous. Okay, so even smartphones, many of them are 64-bit processors now. Yeah, maybe I should point out that these complexity estimates that I'm giving, these are in terms of arithmetic operations on numbers between 0 and b. That's the appropriate measure if b fits within the machine word size. Okay, so this is not the bit complexity. That's realistic for the size of b that we're considering now. If we have 64-bit arithmetic, it would be a lot slower if we were constrained to 32 bits. Second, I forgot to say, yeah, why is this running time only heuristic? Well, it turns out actually the analysis that I described in the previous paragraph is completely rigorous, okay, and it gives you this running time. Where the heuristic analysis comes in is in something that should be lower order of magnitude asymptotically, which is computing cube roots mod p. Okay, that should be linear time on average, but we don't know how to prove that. In fact, we're far from it. Certainly unconditionally, we're very far from that. And even under GRH, you'll be off by a log power factor. Okay, but nevertheless, that should be true, that takes only linear time. In practice, though, it does take a significant chunk of the time, and in fact, it dominates if you don't do it really well. Okay, in my implementation, I think it was at least half the time that was spent doing this, computing cube roots mod p, and so you want the fastest algorithm you can get for that. And needless to say, you know, that of course depends on finding the primes in the first place quickly, so you need fast save for primes. And finally, one other thing that I'll mention, one of the most important points is this Montgomery multiplication. This is after Peter Montgomery. So I mentioned that the bottleneck is computing cube roots mod p quickly. As you can imagine, that involves a lot of mod p arithmetic, and in particular, multiplication mod p is the thing you worry about. Doing that in the most conventional way, if you have two numbers you want to multiply mod p, you would multiply them and then divide by p and take the remainder. Okay, so on an x86, that's two instructions, a mul and a div. One of those instructions is extremely fast. So a fully pipelined 64 by 64 to 128-bit multiplication takes just one clock cycle, which is pretty damn impressive when you think about what it's doing. There's a lot of silicon that goes into making that possible. Okay, the other, division, is extremely slow in comparison. So even on the fastest chips today, it takes tens of nanoseconds to execute. That might not seem like a very long time if you're not used to worrying about tens of nanoseconds here or there, but it really is a long time for just a single instruction. There are good reasons for that. So division is a very complicated operation, and it's done in microcode. Even then, it's hard to get right. So Intel infamously tried to speed up their division instruction in the early 90s, but let's just say it didn't go well, as Thomas nicely discovered. And it ended up costing Intel about $500 million to correct that. I mean, the upshot is, for the time being anyway, division is always going to be a slow instruction and something we need to avoid. That's where this Montgomery multiplication comes in. Montgomery found that with a suitable permutation of the representations of the residue classes mod P, you can turn one multiplication and one division into 3 ordinary multiplications. And that's a huge win here. So you need to address all of these things. You need to be aware of and address all of these things, but they all have solutions if you know what you're doing. All right, so that was the algorithm. Now, as I'm sure all of you know, this was not the end of the story, okay? And as Emmanuel alluded to at the beginning, after finding a representation for 33, 3 cubes problem, there was still one number left up under 100 with no local obstructions and no known solutions, and that was 42. Now, I did search for 42 in the same range as I did for 33, so with the smallest variable up to 10 to the 16, but I didn't find anything. So basically, I had this problem where I knew the answer was 42, but I didn't know the question. And I was going to need a bigger computer in order to find it. And likewise, I also I searched for solutions in the same range for Mordell's question, but didn't find any. But don't panic, because help is on the way, right, in the form of Drew Sutherland. Now, Drew, I'm sure, needs no introduction to this audience, but just for the record, among the many hats that he wears, one is world expert at making number theoretic computations of all kinds, both very fast and large scale. Okay, so he's a great person to have on your team for something like this. Now, it just so happened, the week after the 33 news leaked, Drew and I were both attending the same conference at Princeton, and I managed to convince Drew to agree to 2 things while I was there. One was to join me in this quest on 42, and happily he agreed. The other was to go with me to a Korean karaoke room in Edison. So here's Drew on the right, along with Ralph Schmitz and Akshay Venkatesh and Dave Roberts. I'm sorry, guys, I fully expect to be unfriended after this, but I couldn't resist. Another interesting thing that happened around the same time is that I got lots of offers of help. Okay, so many people had seen the 33 coverage and wanted to pitch in on 42. I ended up turning almost all of them down. So I'm sorry to those people. One offer that we did not turn down, a very generous offer, was from Charity Engine. So they offered us millions of free hours on their planet-size computer, consisting of about 500,000 volunteers with their PCs. Okay, so with the help of Charity Engine and 500,000 volunteers, we found these new solutions to the 3 cubes problem. A solution for 42, which completed the search of Miller and Willett. Is a solution for 3 that answered Mordell's question, and then 2 other solutions that nobody really asked for, but here they are, 165 and 906. Now, as you can imagine, or as you may know, there was a lot of press coverage after this discovery as well for 42. It was a lot like the coverage for 33, maybe, but just turned up to 11. That's how I would describe it. So in fact, I did some radio and television interviews this time around, which is something I never expected to do in my life. Another thing that I never expected but did was to buy a copy of the Daily Mail. You can see there. And they ran this story on page 2. Okay. Now, the Daily Mail, for those who are not familiar with UK press, this is a tabloid newspaper. In fact, it's the #1 selling tabloid newspaper, and this being the UK, that means it's the #1 selling newspaper. Okay. The other thing I wanted to say about the press coverage this time around was, so in spite of the sentiment I expressed earlier about the 33 coverage, I was actually pleasantly surprised by the depth of some of the coverage here. I mean, you might think that the closer you get to mainstream media, the more mangled the message becomes, but that really wasn't the case, at least not universally. I was planning to show a frame capture of a Japanese news broadcast where they spent a good few minutes on this story and covered it in an impressive amount of depth. But seeing as this is being recorded and I don't want to break copyright, I won't do that. In lieu of that, I'll just point out that this is my first project so far that has its own merchandise. So if anyone's really bummed that there's no Ants official t-shirt this year, you can find this one, this 42 shirt on Amazon in the US, or this one on Teespring in the UK. This was made by Brady Heron. Brady's one also has mugs and hoodies. I think I have one of those too. Yeah, there it is. Okay. Anyway, so a bit more seriously, let me talk about, in the last few minutes, some features of our new algorithm. Okay, some of this is stuff that we only thought of after the fact, so after the big runs on Charity Engine. So we weren't in time for that, but it will still be things that are useful for any future searches that people may want to run. Okay, the first was CRT enumeration, and this was suggested by Drew. So remember, I talked about this modulus M that we use to sieve the arithmetic progressions of Z. Well, Drew suggested changing the way that's done. And instead of pre-computing and storing a big table of these, you just internally represent Z as the solution to the congruences, and you work out the Chinese remainder theorem on the fly only when you have to, right? And this turns out to be faster and has several other benefits. So first of all, it eliminates the time-space trade-off. So it's much more memory efficient. And also, because you're representing Z internally or implicitly by this congruence, there's no reason to restrict it to be a machine word anymore. Okay, so you can go beyond 64 bits the size of Z if you want. All right. Third, it gives you much more flexibility in the choice of sieving primes. So in the sieving primes in my case were fixed. They were just the first several primes. Here, you can choose whatever set of primes you want in Drew's implementation. And especially for small values of Z, that means you can afford to spend some time optimizing your choice of this, and that can give a speed boost in those cases. All right, so this combined with some other smaller optimizations that Drew implemented more or less doubled the speed of the core code. So yeah, dude has some skills, but we didn't stop there. Okay, we also considered the constraints implied by cubic reciprocity. So let me explain that. So Castles proved that cubic reciprocity implies that any solution to Mordel's equation, where k equals 3, has to have all the variables congruent mod 9. Okay, and let me be quick to point out, this is a global constraint, not a local one. Okay, so locally you know that they're congruent mod 3, but then the mod 9 constraint is not forced on you. Okay, so that only comes globally through cubic reciprocity. Now, Castle's observation was first recorded just as a footnote in Mordel's 1953 paper. Much later, Colliot-Telen and Wittenberg reinterpreted this phenomenon in the context of Brouwer-Manin obstructions. And what they showed is for any value of k, the 3 cubes equation, there'll be some residue classes that are forbidden globally, but not locally. So the integer solutions, even if there's infinitely many of them, they must fail strong approximation. However, this never rises to the level of an outright obstruction, so to the existence of integer solutions. So there's no Brouwer-Manin obstruction for these varieties. What we care about as computational number theorists, though, is whether we can exploit this in the algorithm. And it turns out that yes, you can. So for k equals 3, it follows that once you fix the value of d, z is then determined mod 81. Whereas if you just ask locally what restrictions are there on z mod 81, it turns out there are 4 possibilities. So in a nutshell, the cubic reciprocity constraints cut down the solution space by a factor of 4, right? Now in our paper, we extended that analysis to all k that are plus or minus 3 mod 9. And again, we find some congruence constraints on z mod some modulus q that divides 27k. So actually, I did already use this in my original search when I was searching not for 33, but for 3 up to height 10 to the 16. I didn't use it for any other value of k because in my implementation, it wasn't worthwhile to do so. What makes it worthwhile in Drew's implementation is the more flexible choice of sieving primes. Okay, so without that, basically this modulus q interferes with the choice of sieving primes. Okay, so it is never again the case that you get as big of an improvement as you do for k equals 3. You never get a factor of 4 again, but it's always something. Well, in fact, for some values of k, the global constraint barely registers. Okay, this doesn't help much at all. But what we discovered is that there are extra 3-edit constraints that I wasn't exploiting that always do help as well. So even just looking at solutions mod 81 as opposed to mod 9 always gives you at least a factor of 2 reduction in the size of the solution space. Okay, so this helps. All right, and a third optimization that we did, and maybe most significant, is to change the box shape. And so we look for solutions where we think they're most likely to be. Okay, here's what I mean by that. So as I described the algorithm, you have to do all values of d up to this number of cubed root of 2 minus 1 times b. Okay, now that's pretty expensive because you end up testing, well, for 90% of the values of d, the largest 90%, you have only a very short arithmetic progression of z's to test. And remember how I said the bottleneck is in computing cube roots mod p. Well, all of that's just in the setup cost to get to this stage. So for each d, you're doing a lot of setup and then testing very few values of z. Okay, so that's inefficient. So it turns out that it's more efficient than to give up on the exhaustive search and decouple the ranges of d and z. Okay, so we explored that. A good example of this is in our solution for k equals 3. A good example, an extreme example, as it turns out. Okay, for that, we have this ratio less than 10 to the minus 6. So here the denominator is telling you how far you would have to take d in an exhaustive search in order to guarantee that you'd find the solution that we found. Okay, and this ratio being less than 10 to the minus 6, what that tells you is that in principle, at least, if you knew to do this, if you knew to take such a skewed box, you could find this solution with a search space that's 1,000,000 times smaller than the one for the exhaustive search. Okay, of course, that's a big if. You don't know this ratio in advance. And in fact, we did some statistical analysis that indicates that the solution for 3 that we found is something like a 1 in 1,000 event. Okay, so we were very lucky to find it. I should have said, this is another case where the constraint being only on the side of the smallest variable is very important. They were like size 10 to the 21 for x and y in the solution for k equals 3. Right, so you wouldn't normally pick such a skewed box shape. Nevertheless, I think this illustrates the point that there are gains to be had by abandoning the exhaustive search and exploring different box shapes. Of course, that raises the question, well, once they're decoupled, how do you then choose these parameters? Well, basically, you want to maximize your chance of finding a solution within a given number of clock cycles. Okay? The input that you need for that is some kind of probabilistic model of the ratio, d over z. So what are the likely values of d over z? If you have that together with some measurement of your actual code, so how fast can you increase the bound on z relative to an increase in d, that kind of thing. You put those two together, then you can answer this, this optimization problem. And we did that. I won't go into the details at all. You can find them in our paper in the archive. I'll just say that in a nutshell, the heuristic for this ratio is that it acts like random points on the real variety. Okay, so you end up studying the real density of points on the Fermat cubic. All right. So all of these optimizations, if you put them together, here's what you end up with. It makes the search about 25 times faster than my original search for 33. Now, in fairness to myself, this is an apples and oranges comparison, again, because of the different box shape. All right, but what I mean is if you took the range for z to be the same, 10 to the 16, as I did, but you cut the range for d shorter to what our analysis indicated is the optimum, then you would indeed find the solution, and you'd find it in about 1/25 the time. Okay. Moreover, so with reasonable parameter choices, our new algorithm can find all the solutions that we found in under 50 core years total. I mean total time here. This is a pretty conservative estimate. It takes into account all the unsuccessful searches that we did for other numbers, for instance. And even then, so half a core century is nothing to turn your nose up at. But on the other hand, it's less than half of what I did just on our university supercomputer in the initial search for all these numbers up to height 10 to the 16. Okay, so it's not an extreme computation by today's standards. Right. Okay, there's one other thing I wanted to tell you about in the last few minutes here, and that's Heath-Brown's conjecture we also tested. So there's pretty good evidence now for the qualitative form of Heath-Brown's conjecture, that solutions exist when they should. Okay, but Heath-Brown went well beyond that. He made a quantitative conjecture that the number of solutions of height up to b for any fixed value of k is asymptotic to a certain constant, well, a certain number depending on k, times log b. His guess for this is the, what you would put in if you just plug in the Hardy-Littlewood heuristics. So he's conjecturing that even though the solutions fail strong approximation, that's kind of a lower order correction. So the leading order asymptotic should not change. Okay, that was his conjecture. And as part of our analysis, we computed these densities to pretty decent precision, okay, better than double precision. And that allowed us to compare Heath-Brown's prediction against actual counts of data that were compiled by Huisman. So I remember he found the solutions for all k under 1,000 of height up to 10 to the 15. Okay, the difficulty here is it's very hard to test this conjecture for just a single k because you never get enough solutions to make a meaningful comparison. But the point is, if you amalgamate a whole bunch of k, like all the k under 1,000, then you can make a nice comparison, and here's what that looks like. So here on the x-axis, I'm plotting b, the height bounds, on a log scale between 10 to the 7.5 and 10 to the 15. Okay. The vertical axis plots the number of solutions that you find in that box for all k, all cube-free k under 1,000. Notice the fit is perfect, pretty much. Yeah, against the line that Heath-Brown's conjecture would predict. Actually, to be a little bit clearer, the conjecture only predicts the slope of this line, and we fit the y-intercept to the data. But still, I regard this as very strong evidence in favor of Heath-Brown's conjecture, and I think it's the first of its kind. So finally, let me just tell you, you never finish with this problem until somebody solves it. Okay, even after our searches, there are still 8 candidate values of k under 1,000 with no known 3-cube representations. Here they are. For comparison, remember that Miller and Willett programmed the EDSAC in 1954. And I think it's interesting to note that they found representations for all but 9 values of k under 100. Okay. However, it took another 65 years to complete that search, okay, and vast increases in computer technology. All this is to say, I don't think people should stop looking. In fact, maybe we need to make an 8 or bust project or something to expose this to the wider community. Okay, but I'm not going to hold my breath at finding solutions for all of these anytime soon. Right. Second, so there are other analogs that one can look at. So this 3 cubes problem, as I mentioned before, is in close analogy to the sum of 3 squares, Legendre's theorem. There's another classical theorem along these lines, which is Gauss's Eureka theorem, that every positive integer is the sum of 3 triangular numbers. Okay, and the most direct analog of that would be the sum of 3 binomial coefficients, like this, with 3s instead of 2s. And I'll just note that a similar algorithm would apply, except that instead of finding cube roots mod d, you would solve this polynomial equation, z cubed minus z congruent to 6k mod d. Much of it's the same. You'd use, instead of Shanks-Tonelli, you'd have to use something more complicated, but it should still be roughly the same. So somebody should do that. Finally, I'm going to share one other future challenge. When I shared the news with 33 Discovery, it actually on the day, it so happened that Roger Heath-Brown was in Bristol to give a talk. I shared the news with him over a pint at the Nettle and Rye. One of his first questions was, well, what about x cubed plus y cubed plus 2z cubed? Okay, so here the point is that there are no local obstructions. So this is like the simplest diagonal cubic you can write down with no local obstructions. Yeah, so this is another thing that people have looked at. Well, in this case, it wasn't too much of a modification to change the code. and Drew did that, okay? And we found these solutions. So we found 5 solutions for 3 numbers that had no previously known solutions for this. But that still leaves 4 numbers under 10,000 with no known representations. And here they are. Okay, so that's it for the mathematical content. I'll just leave you 1 slide of Zen to consider. So thank you for your attention, and I'll take any questions that you may have.